Hello guys, today we are going to discuss this problem, letter combination of phone numbers, problem number 17 on Leet code. And this is one of the variation of a problem. We find this problem at lot many places, and hence we are going to discuss this. So the problem is something like this, that we are given a keypad of a phone number, and every digit, that is 2, 3, 4, 5, 6, 7, 8, 9, represents some alphabets. For example, 2 represents ABC, 3 represents DEF, and so on. And the problem says is that if somebody presses two digits, for example, 2 and 3, so what all total combinations of word can be formed? For example, A, if he presses 2, and then one time, so A will be generated, and 3 one time, D will be generated. If he presses 2 two times, then B will be generated, and 3 one time, D will be generated, and so on. So if we see here, all these combinations are possible. Uh, that is AD, AE. A can be combined with D, A can be combined with E, A can be combined with F. Similarly, B can be combined with all of these. So these combinations are possible. So whenever we have a problem, something which says as combinations, permutations, or something as Sudoku or an queen problem, then definitely that's a problem of a backtracking. That's a backtracking problem because we have to find all the possible paths from starting node and cover every possible combination in this case. So let me open up um, the code. Okay, so this is the code. I'm using backtracking, and backtracking actually has a pattern, or we can say a backtracking template. So these are some kind of problems which can be solved using backtracking. So in backtracking, we have all kinds of combinations which can be solved with backtracking. Then we have generate all parentheses, n queen problem. Then we have permutation problems. Then Sudoku solver. Then word search. These are some of the examples of backtracking. So I have already covered what is backtracking and what is backtracking template in one of my video. You can check that. So basically, what happens in backtracking is we start with a candidate and we create an empty candidate. Then we call the backtracking recursive backtracking function, and we provide the first candidate to the backtracking function. In backtrack function, we take a base case, and then we iterate through all the candidates which are possible to be that can be placed on the candidate list. And whenever we find um, like we place every candidate, then we backtrack, call this recursive backtrack, and we move to the next candidate. And if the solution is find, that is a base case is hit, we actually note down the final solution here, something, and then we remove the last added candidate. So that's how we are going to solve this. So let's see first of all what is a recursive backtrack tree for 2, 3, 4. So 2 will be represented as ABC, 3 will be represented as DEF, and 4 will be represented as GHI. So backtrack tree will be that we can append D to A, so it will become AD. Then after that, we'll have G to AD, so it will become ADG. And what will happen is, let me just go in here. So first we'll have A, then we'll have AD, and then we'll, in the third backtrack function, we'll have ADG. Now the condition is met. So condition in this case is this one, that is if the candidate size, so this is the candidate size, is equal to the input size. So input size is 1, 2, 3, and it's equal. So we'll just push back and return. So while returning, when we return back, we remove the last added candidate, that is last added letter. So I'll remove this G here. Let me go back. So I'll remove this G. So now it'll become AD again. So it comes back again. And I'll add another letter, that is ADH. Then again the condition is satisfied that this size becomes equal to the input size, that is 3, and I know we note it. And then we again pop back the last, and then we have AD, and then we go back to AD, and then we add ADI. And similarly, for AE, we can have the similar backtrack tree. For AF, we can have, then for B and for C. So let's go to the code directly. So what we are going to do is we are first of all creating a map. So in a map, we'll have a letter and a and like it's a digit and the alphabets to which it corresponds. And we'll have an empty candidate list. Then we'll have the recursive backtrack function. This is very simple backtrack problem, no variations, very simple. And then we start with the index 0. So index 0 means here is that if we have input as 1 2 3 or maybe 2 3 4, I'll say, because 1 is not allowed. So if we have something as 2 3 4, so we'll start at the index 0, which means this 2. So this is the index, and this is 1 and this is 2. Okay, so now what will happen is we'll just find whether the input start index. So in this case, this will be 2. Whether I'm able to find this in an ordered map. So yes, I'm able to find it. I'll return ABC. So now I'll have this letters of numbers. In this case, will become as ABC. So now what I'll do is I'll iterate through all the possible candidates. So this size is 3. So I'll go from I equal to 0. So candidate will be equal to letter of numbers I. So I'll have my first candidate, which is equal to A. And then I call recursive backtrack function with start index plus 1. Start index was 0 earlier, and A. So now it again, okay, let me just make something like this. Okay, this is in a for loop for I equal to 0 to 3. So now it reaches into the recursive backtrack function, which is one end A, the candidate. It will check whether the base case is reached, no, and it will find the entry for the first index. So first index 3 here, and the entry found here, that is will be for 3 we'll find DEF. So it will come as DEF, and I'll start from I equal to 0 to I smaller than 3. So in this case, I'll append candidate is equal to AD, and then I'll do recursive backtrack. Start index plus 1. Start index was 1 here, so I'll do it 2, and then I'll pass the candidate AD, and let us reach the function recursive backtrack 2 and AD. I'll find and so I'll have this one, that is input start index. So now we are at start index 2, so I'll find 4. So for 4, I'll have GHI, and again I'll have I equal to 0 to I smaller than 3, and candidate will become ADG, and then I'll do recursive backtrack start index plus 1, and it will be ADG. So now in this case, our base case will be hit. So in this case, candidate is ADG, while the input is 1 2 3. So 2 3 4. So sizes are same. I'll just push back. So now what will happen is, in the next statement, the last letter will be popped. So it will become index will be equal to 1, and my candidate will become AD. So at index I equal to 1, I'll again push one candidate, which will be H. So now I'll do a recursive backtrack 3 and ADH, and similarly and so on. So all the combinations are actually searched or traversed using this recursive backtrack function. So let us see the time complexity of this backtrack algorithm. So basically, people struggle in finding the time complexity. So in order to find backtrack time complexity, you should first visualize complete backtrack tree. So now in this case, if we see, we have 27 nodes generated. For example, for these three letter or digits, 2 3 4, and again these three digits have only three letters uh, to represent. So this 2 can generate total 9 combinations. Sorry, this A can generate total 9 combinations. This B can generate 9 combinations, and then this C can generate 9 combinations. So it will be total 27. So if you'll see, if we have only digit 2, so we can have only 3 combinations. If you have digit 2, 3, then we can have 9 combinations. If you have digit 2, 3, 4, then we can have total 27 combinations, right? Which we have seen in above example. And if you have digit 2, 3, 4, 5, we can have 81 combinations. So the precondition is that all these four digits, 4, 2, 3, 4, 5, each digit represents only a uh, three alphabet, only represent three alphabets. So in that case, it will be 3 raised to power 4. So the time complexity would be number of digits. So in this case, number of digits would be n. This is 4. And m is alphabets in the digits. So 3 is the alphabets. So m raised to power n is the time complexity. So now let's go to the time complexity for the 4-digit numbers. So if we have 7, it represents the four alphabets, PQRS. So in this case, the time complexity goes like this. In case of 1, we'll have 4 raised to power 1. So this is the alphabets in a digit. And similarly, for 4 digits, having 4 alphabets per digit, we'll have 4 raised to power 4. But in case of a mixed digits, for example, in 2 7, 2 represents 3 alphabets represented by 3 alphabets, while 7 is represented by 4 alphabets. So the time complexity would be the multiplication, 3 into 4. For example, 277. So the time complexity would be the number of digits in number of alphabets in 2, which is equal to 3, multiplied by number of digit alphabets in 7, 7 and 7, which will be 444. So anyhow, the max time complexity we will take, which is m raised to power n, because if we have 4 digits and each digit represents 4 alphabets, is represented by 4 alphabets, then it will be equal to 4 raised to power 4, which comes out to 256, and this is 192. So this is lesser than 256, and the space complexity would be n because in the recursive stack, if we see, the maximum uh, candidate which can be formed at any time in the recursive backtrack function would be of size on, and n here can be max 4 in this case. So that's why the space complexity would be on in this case. So that's all for this video. Thanks a lot. Have a good day.